Okay, so welcome everybody to the fourth tutorial that we have here. This one's going to be a little bit different just because it's going to be focusing more on the paper that we talked about. So Chris Denisius and assuming our guest Leonara. So how much have you guys read? I know Chris, you said you've read it. Denisius, maybe a little bit.
I read it at the beginning of the course. I don't know how much they are.
Okay, and Leonard, I'm assuming none. Okay, well, no worries. We'll go through a short explanation. We'll talk a little bit about paper just to like catch everyone up and have everyone on the same page about what's actually happening in the paper. And then we're going to try and like look at the probabilities a little bit more and see if that might get like a little bit different emphasis on what is actually happening in the paper. So just for my own fun, just so I don't have to talk, does anyone want to try and give a brief explanation or like summary of what the paper is talking about, just part by part, or?
Sure.
Sure.
Basically, he's talking about, I guess, a device that is used to show some sort of phenomenon. I don't know how much to go into it.
No worries.
The device consists of like three parts: two detectors and one emitter. And when the emitter sends out two particles, and the detectors kind of flash lights, and then analyzing, I guess, the input-output, you can see certain patterns. And Einstein uses that to try and prove certain things. It seems like that's disproven in the end. So that's mainly the whole thing, talking about the device and trying to show this phenomenon, which seems to be quantum entanglement.
Right. Yeah, that's the word that he kind of skates around, is the word entanglement around the entirety of the thing. But yeah, pretty much exactly what you said, Chris. I'll just throw it up on like a pictorial example, just to even though there's much nicer diagrams, I'll try and draw something. Pretty much exactly what you said. We have a device that is some sort of magic box that we're trying not to worry too much about the details. That's got two lights on the sides and then three possible settings. Let's say it's switch to the first setting and then 1, 2, and then 3. And then you have a possible like input for a particle that goes in. So yeah, that's the first thing. Or we could say even multiple particles that are supposed to go into that thing. So yeah, detector of some kind. And then we have, as shown in the box up there, we have a detector on either side, and then particles emitting would say you push a button at the actual emission device C. And the question is, what do we expect to happen based on the idea that these detectors will flash a different light given a certain particle? And then what are some of the assumptions that we have to make given some of those settings?
It's very heavily stressed that they're not connected.
Yes, and yeah, that's a good point. Yeah, we were talking about that earlier. Yes, they're not connected in any way. Imagine that there is, I think they even show like a bot, like he's very explicit. He goes a couple pages to be like, all right, there's no way that these two devices are connected. It is like isolated as far as we can tell, different universes, if you want to even say that. There's no way that these devices are talking to each other mechanically, electrically, anything like that. So yeah, it goes over that a lot, but I guess that's an important point to be like, there's no way that we can visibly see that they are talking to each other. So yeah, if anyone wants to, let's get into a little bit of the like notation and everything like that. So each of these two boxes have three settings, as you can see. So we can imagine, here I'm giving the answer away a little bit, but I'll just scroll down. So you can imagine, since we have two detectors, each one with three different settings, we can think about the different combinations of the settings. It says in the paper that each time the settings are set to a random one, so we don't know ahead of time what the settings are. But we can actually like go through the different possibilities, much like binary, just like doing the different settings. So we're going to say detector 1, if I can spell, detector 1, and then detector 2. And then we're going to have the different settings. So it's going to go through different possibilities, like detector 1 is set to 1, detector 2 is set to 1, then we'll have 1 is set to 1, 2 is set to 2, and then so on and so forth. So then 1 could be 3, and then we have all the different possibilities where the first one is 2, and then the different possibilities where the first one is 3, 3, 2, 3, 3. So if you count them up, it's about 9 different possibilities for the different settings in there, which makes about sense. There's 3 by 3, so that means that you multiply them, there should be about 9 different possibilities for what these detectors are actually set to. So then he goes through, and let's see if they have a better picture here, but I don't think they actually do. I'll stick with this picture illustratively. When an actual particle goes into the box itself, the light is going to flash either red or green, sort of based on the settings. And I don't want to say this, but also like the way I interpret it, sort of based on the particle. So we'll say we'll have one like particle, like the same particle comes out of the box. It goes into the left one, and that one's set to 3, and then it goes into the right one. It's set to 2. The one on the left will flash red, and the one on the right will flash green for some reason. So like we're assuming that there is some sort of tie between the particle and the particle state and the setting of the machine, or the setting of the detector, and what the actual flash is itself. So that's one of the assumptions that we kind of make, is that something encoded in this particle, who knows the spin, the magnetization, something with the setting causes this detector to flash a certain state. So the way that they go through and say that, yeah, the device settings are denoted with a 1, 1, to say they're both in setting 1, and then the actual flashing of the colors is set to like RG. So that means like R would be the first device, or the device on the left is set like flashes red, and the second device flashes to green. So if we were to enumerate the different possibilities that come out of that, there should be how many possibilities, if there of like different colors, would there be for each of the devices? That was an open question. Sorry.
Like you're talking about like together.
Together, including we're enumerating over like the order doesn't matter, or the order does matter of each of them. How many different possibilities are there?
Yeah, shit. RG, GR, GG, R.
Those are the two, but then you also have to take the case where it's RG, and then, wait. Yeah, no, it is 4. What am I thinking? Oh, wait. Oh, no, I'm sorry. I was thinking of something different. Yes, 4 possibilities. Yes, you're absolutely right. Yeah, you're not crazy. Yes, so yeah, there should be theoretically 4 different possibilities that actually show up. So we'll go through the different device light states, or light emissions, if I can spell emissions properly. And then, so yeah, detector 1 will be, and then we'll have detector 2. So we'll do that one, stay R, G, and then order matters, so RGR, and then GG. So one's flashing red, one's flashing green, got different combinations of those two. Okay, so we have a typical, like they show just a little record fragment. If you were to do this experiment a bunch of times and you record the different settings and record the different lights, then you would say like, okay, we can make like a good analysis of what this box is actually doing. So then once you accumulate the data, what he goes through and states that there are some situations where the detector is in the same setting. So for example, assuming that the particle has encoded with this information and the same setting will always give the same light color, that means that if both the boxes are set to the same setting, then theoretically they should both give the same light output. So let's just draw a little example in my notebook here. So if we have a detector on the left, and it's set to state setting 1, which is, I'll put it all the way to the left, and horrible drawing, but you get kind of what I'm going for. And then the other device, it is also set to 1, there. Then this, if the left one the right one flashes red, if red's on top, then the left one should also flash red, and it should not be green. So if a device is in the same setting, we can say with a certain probability that it's got to be one of the two, either red, red, or green, green, depending on what that is. So of those, sorry, I'll go back to the actual paper here. So of those possibilities there, with the case settings where they're both set the same, that is 3 of the possible 9 combinations. So that is 1/3 of the actual of our enumerated possibilities. So here we have 1, 1, 2, 2, and 3, 3. Those we should assume that they should always give some combination of red, red, or green, green. So that's at least a little bit of the possibilities out of the way. Then in the other case, we have where the machines are set to different settings, say 1, 2, or 1, 3, as he goes through. If there's different settings, then basically there's only a 1 1/4 chance that those different settings should give the actual same color itself. And that 1 1/4 chance is just based off of that there's 4 different possibilities. So if there's 4 different possibilities, say they're set to random settings, we don't know what ahead of time it is, 1/4 of the time they should flash the same for the rest of these right here. So through those different combinations, I will put them in red. So yeah, anything in yellow should be, so the yellow should be same no matter what. And anything in red, we have that it should 1/4 of the time flashes the same color. So yeah, here.
I thought it was 1/3.
Shouldn't it be the same flash, same color, only a quarter of the time? We're getting to the part where it's going to be like it's going to be a weird not a quarter of the time. Then that's going to be it. Because yeah, we're still thinking of them as classical particles here. So if you go through the different possibilities, there is see, there's 1, 2, 3, 4, 5, 6 different like remaining possible states. And if you think that each one should be encoded, then should only like how do I try and explain this? Yeah, so if each setting has a probability of R and G of a half, and then you multiply that together, it should be a quarter. Let me try and think of actually, yeah, I always get messed up with the probabilities sometimes too of why it should be. I know at the end that the state is will be that it will be 1/3 together, but at least for this like subcase scenario, it's a quarter.
Oh, I thought I was under the understanding that it was for case B. I thought it was that they actually detect 1/4, but it should have been 1/3 because the way they describe it, like if you have at least with the instruction set,
Right.
The instruction set belief it should be 1/3.
Right. Let me make sure that is. I'm pretty sure it was the opposite, but also yeah, it's been a couple weeks since I've read this, so let me. Yeah, because in the start he says, where does he say it? That it should be 1/3. Hold on, 1/3. The 1/3 last part of the device. No colors.
I'm not sure if you just in the third of the cases that B runs.
Will detect a flash same color. In a third of the case, B runs particles carry the instruction set. Right, because yeah, we're still talking about classically here. So yeah, I'm just trying to figure out, yeah, why would it be 1/3 then if it is that?
So the way I got it for the instruction set one is if you have the instruction set, if any of there's 6 different options. Is this it?
6 different like ones where there are different possibilities. 6 out of the 9 are
Yeah, 6 out
different.
of the 9, but the settings are different, right?
Yes.
And the possible instruction set, any of them where they have 2 of the same color, then it's 2 out of 6 times that the same color should flash. So it'd be 1 out of 3rd chance that the same color should flash.
Yeah. Okay, you're absolutely right. Then what was he talking about in case B there?
So my understanding was that 1/4 is the actual probability that actually happens.
The actual like quantum mechanical
the
probability.
that they got.
Yeah.
But it should be 1/3. So it was like where did the extra?
Yeah, where does the actual difference come from? Okay, I'm sorry. Yeah, you're right. This was the quantum mechanical part of the section, and the actual one should be 1/3. Okay, let's work through. Yeah, like why it should be 1/3, and then we'll go from there. That's my bad. Yeah, you are completely right that it should be 1/3 of the time. Okay, yeah. Let me rephrase that because yeah, you're right. I was thinking about it in a way that was incorrect. Okay, yeah. So yeah, because it's like 6 different possibilities, and then 1/4 of the time they will flash the same color. So then 6 times that, then it should be that like 2 out of the 6 should 2 of these 6 combinations should be the same, which is equal to 1/3. Yes. Okay. Thank you, Chris. I forgot about that part. Okay. Yeah. So the part where they aren't the same, it's 1/3 that they do flash the same, and then it's in quantum mechanical, and that's if it's classically, and then 1/4 if it's quantum mechanical or the actual occurrence that they flip. Yeah. So let's work through why it should be 1/3. It should be 1/3. Yeah. So do you want to work me through the logic then, Chris? Why should it be 1/3 of the time it flashes the same?
Okay, sure. So so they were considering that the particles had instruction sets.
Right.
And they would be written in like G, 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 R, G, something.
Yes.
Which basically means that the first G is if the switch is in the first position, it'll flash green. If the switch is in the second position, it'll flash the second color, then the third one subsequently.
Right.
So assuming that both particles had the same instruction set, if they had a case like G, G, R, so 2 things the same, there's 2 options, either 1, 2 or 2, 1, where they'll flash the same color.
Right.
So that is 1/3 of the time in that case, because there's 6 different options that they could have. 1/3 of the time, they would have the same color flashing.
Right.
As far as I know.
No, that makes complete and total sense. Yeah, I completely forgot to like go over the instruction set, so that's where I was getting the confusion. Okay, yeah. So like yeah, in the paper they talked about the idea of instruction sets. Sorry, I'm just reiterating what you said there, Chris. So they're assuming that the particle is encoded with some sort of combination where it will, with a given setting, flash the actual color. So if like there's three different settings. So each of these instruction sets must have a color associated with each of those settings. So that means we can go over the different possibilities for what the different instruction sets are. So for example, an instruction set, like you said, could be RRR, which means for no matter any of the settings, it should flash green. So for settings 1, 2, or 3, it should flash red. Right. Okay. So then we can go over the different possibilities of what the instruction sets are. Instruction set possibilities. Right. So we can have a place that's no matter what, it's all going to be R. Actually, let's go through. Actually, let's put this in a table. Setting 1, setting 2, and setting 3. The first possibility is that for all the settings they'll be red. Then if not, they'll be green. And then all the different like just counting up essentially in binary, but instead of true and false, it's red and green. So then repeat this, it'll be green, red, red, green, red, green, 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 red, and green, green, green. So yeah, that should give us all our different possibilities for the different instruction sets. Absolutely. Um, so yeah, there's the two cases where no matter what the setting is, all the settings will provide it as an actual like flash of the same color, and so those are red, 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 and green, green, green. So those are two of our different eight possibilities. And then for the rest of them, like Chris had mentioned, that there is sometimes depending on the setting, it will always either be that two are a certain color or two are like either two greens or two reds in the combination. So that means that 2/3 of the time it will be the flash, depending on if it is on the right setting or not. So that means that there should be 2 of the 6 combinations should get out there, if I'm following what you're saying.
I can't help it.
Oh, sorry, I might have been just like word souped it.
So I was thinking, so the two before, except for the 2 times you highlighted,
Yeah.
it should always have 2 of the same color
Right.
for possible switches.
Yes, it'll always have a red, red, or a green, green somewhere.
And so if you consider those, like the 2 reds being 1 and 2,
Yeah.
if you look at the possible switch combinations that aren't the same switch, the ones in red that you highlighted.
Yes.
If you look at those, 2 out of those 6 would be possible in each one of the double combinations. So if you have RRG,
Right.
that means you could have the pairing 1, 2 for the detector, or the pairing 2, 1 for the detector.
Yeah. Okay.
To flash red.
That makes sense.
If you have any of the other ones, you can do the same thing. It'd be 2, 3, or 3, 2. So you'd always get a 1 out of 3 chance that you'd get the same color flashing. And
Right.
then actually, I forgot they actually mentioned this too. So that gives you 1 out of 3. But then you also have to factor the 2 yellow cases that you added, the all red and all green.
Yeah.
Those 2. So
Yes.
that it actually should be, they said minimum 1/3. You should have actually a little bit more, because if they do have exactly red, 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 then you should always flash the same color too.
Right. So yeah, just to reiterate what you're saying. So what you're saying is basically the possibilities where, say, we'll take the 1-2 case where like the settings are set to 1 and 2. Then we have all these different possibilities that might be able to come in here for that. You have the actual what the settings are, and then when the instruction sets are. So RRG is possible setting for the actual thing, or you have 1-2 RGR, or et cetera, et cetera. 1-2. Then next one RGG. 1-2 GRR, and then 1-2 GRG, and then 1-2 GGR. And yeah, we're not considering the possibilities where there is like they're all green or all red, because we're just doing like a base case analysis. So if we take the cases where they're going to flash the same, it's going to be one where it's the RR there, not 1-2, 1-2, 1-2, 1-2, and then 1 there. So like you said, 2 out of the 6, like for a given setting, should give an actual, like 2 out of these 6, 6 give the same color. And that's the both having the instruction set combinations and then the actual color set, or then the actual detector settings for any given detector settings. So yeah, like Chris mentioned, that means that 1/3 of all different, like when the different settings on the boxes should give the same color. So yeah, that now makes complete total sense. Sorry that I got diverted on with forgetting the instruction sets. Okay, so yeah, now we observed that at least a little bit more than 1/3 of all buttons pressed should give the same color when it has happened. But the problem is, and the quantum mystery that the paper gets at, is that it's actually less than 1/3. It's 1/4 that shows up in like probability. Like when you actually do all the experiments, 1/4 of them show up as the same color in reality. And that is the quantum mechanical mystery, is like how can these two particle, or like given the particle probabilities for a classical situation, it's less than what the expected actual probability is in reality. So that is the quantum mysteries. And so I'm curious, we were talking a little bit about some of the interpretations earlier with Einstein and stuff like that. Did you want to bring that up? Just because, yeah, I've gone through the actual explanation of the paper, so what were some of the interpretations that were given based off of this in the paper?
So Einstein seemed to have interpreted as the particles deliver some sort of instruction set, like we were talking.
Right.
But given that we deduced that it should be linear, it's not. So most other people believe that there must be some sort of underlying connection that we're not seeing. And they seem to go into detail of whether the connections are actually there, whether they're only there when we measure them, and more, I guess, of other quantum mechanics mysteries of just stuff like that. And that's pretty much all I guess we want.
Yeah, no, absolutely. So yeah, that gets into the little bit of the a pseudo-physics, pseudo-philosophy, as I was kind of talking about. There's different interpretations of the actual situation. Since the theory doesn't match up with the reality, how can we reconcile this difference? And one of them is that the instruction set theory is correct, but there's something that we can't interpret in there that is weird. There's something else going on. No matter how isolated we wanted these two systems to be, they weren't isolated for some reason. That the instruction, so like it's not that the instruction set theory isn't there, isn't correct, and there's something else going on. And there's a debate where Einstein is on one side of this, and then the actual what is actually happening is on, and they accepted within the community is a different side. So the interpretation of what this actually means is where it gets a little bit into the which side were you on back in the actual when quantum mechanics was already going through and being formulated. And different people had different interpretations, and then it was Max Born. I think they mentioned him later in the paper that came out with one of the more accepted interpretations that we currently run in quantum mechanics these days. So it's and that has I don't want to get too much in the philosophy, but it's always interesting to talk about does observation and change this superposition state, this entanglement state, and with that observation through measurement, what is actually happening at a base level? Why does, when we look at something, it seem to change the outcome of it? There's a lot of that going on in this. And this paper tries to go in at a very high level. It's kind of a bit confusing, but it's definitely worth the read. And sorry, I'm just rambling now, but that was the parts that I was trying to get at. That there's different interpretations, and we still, even though quantum mechanics is so well proven, you could still take different sides of what the actual experiment is happening. So what was the third point I wanted to talk about? So it was Einstein, and then Bohr, and then the Bell, which is the guy who made Bell's inequality, were all these key figures back in the day talking about what is actually going on, what is the correct interpretation. So it was quite the debacle back there, and eventually we came to our current interpretation of quantum mechanics, which is that there is some sort of entanglement happening. There is no communication so something is happening. The one thing they don't mention in the paper that is a key point that maybe Dr. Sabri might want to bring up is, it's you got to make sure to not call whatever is happening communication. There's like an explicit no communication theorem. I'll actually write that down in quantum mechanics. The no communication theorem. This won't be like on any tests or like I don't know if Dr. Sabri will cover it in the course, but explicitly there is a theorem that states that even though these quantum mechanical particles are entangled and you could send them to across the other ends of the universe, that when one is measured and causes the other ones to happen, there's no way that you can actually use that as a communication method. So there's no way we can get information to travel faster than the speed of light using entanglement. It's always just going to be information that would have been known anyways given measuring one of these particles. So it's a bit weird to wrap your hand around because you think, oh, hey, like entanglement, can't we use that to like send some sort of faster than light communication between us and Mars? And according to the theorem, no, that's not an actual like way. We can't exploit entanglement to get like something that communicates faster than light, unfortunately. So yeah, so little side bit if you're ever thinking like, I wish we could use entanglement for something cool. No, unfortunately, that is there's no free lunch in physics. Yeah. So, any other thoughts on the paper or any like questions? I know we had some questions on like the interpretations, Chris, but anything else that you guys had at Ignatius or?
Yeah, did they like actually build this machine? Is that why like when they actually measured the result, it's like 1/4 instead of like the theoretical 1/3?
So I'm not sure where they said in the paper. I'm not sure if they built this explicit machine. I think this machine was more of like a case of like showing the actual problem itself. But they've designed machines analogous to this problem, where there's an expected result, and then there's an actual result that is different.
And so this machine is basically built off of those experiments that they've done in the past, which is not explicitly this machine, but it's like kind of related to that because like the results are like 1/4 and they expected like 1/3.
Yeah, I think they did that. I think Einstein, Podolsky, and Rosen did this experiment. That's from my understanding. It might have been his exact machine because he said he could build the machine at the beginning. He said it's possible. He just doesn't have the money or resources.
Yeah, exactly.
I think it's conceptually the same as this. Yeah, there was this weird word, this Gedanken.
Yeah, the Gedanken experiment, which I'm sure we could look up if you want to. I'm also curious what it actually was, but yeah, similar enough with like probably because how the heck would you build like a machine that is like isolated from the Earth and isolated from all this stuff? So yeah, it's more of an engineering challenge than an actual like conceptual challenge. So this is just conceptually similar. But yeah, I'm interested what this Gedanken experiment is because I don't know if either of you guys or anyone looked that up.
I think he was also mentioning how there's other connections that might be there. Like if you put this machine on a table, they're technically connected through the table and they could like vibrate, but we're not, I guess, designing it to do that. So
yeah, exactly. Okay, so this is like a thought experiment, is I think what the Gedanken means, and that's probably just the German word for like thought experiment. So it's
maybe it was a thought experiment.
Yeah, I'm not sure. Either way, we know that this like has been like experimentally tested. So as I was telling Chris, I know that quantum mechanics like they tested it down to like so many x decimal points. So we know that the actual like measurement of 1/4 is the actual measurement. We just like it hasn't been built in this way. I'm not sure what the actual experiment was that they ran, or whether it was just a conceptual experiment. But yeah.
So they're just saying like if they didn't build it, like that's the result you're going to get.
Yeah, exactly. Yeah, we've done other things that makes us think that this is exactly what the result we would get. Yeah. But hey, if either of you guys want to go out and build a machine, I'm sure. Capstone build this extremely isolated machine.
So there's no way to use quantum entanglement at all for communication? I thought that was one of the things that like quantum computing was hoping to take advantage of.
Like they're trying to take advantage at least in other ways, but it's not in faster than light communication or like non-causal communication is what they would say. So yeah, they're trying to use like the properties of entanglement for like we were showing some of the algorithms, but it's not the actual like communication of entanglement side that they were trying to get at. So yeah, if we could, we would be exploiting that, but we're not there yet. Yeah.
So they do use like entanglement in other aspects. You're saying like some algorithms that use it.
Yeah, I think so. I'm not exactly sure what the algorithms are, but I know at least from other courses I've taken that like and having like if you guys ever heard of quantum key distribution, which is it's so essentially there's this idea out there that you can pass keys securely and have like a different form that is like not breakable, because right now we do RSA factoring, but there is a way that we can pass it using a quantum entangled particle to pass a certain distribution of key, and that takes advantage of the fact that the particle is entangled. If you're going to ask me how that works, I know that it's just a current active source of research where you pass like sets of photons to different people, and since they're entangled, we can know one thing versus another, and know that there hasn't been anyone listening on that line. So it's a whole like information theory thing. So yeah, maybe I'm not sure about like Shor's algorithm or anything like that. I don't know if that takes entanglement, but there are things that we can use entanglement for in quantum computing. So yeah, it's all okay. If you want to start reading into it, there's a lot that you can go into, but it's like again, it's hard to get it without like this paper shows without going too heavily into the math and the formalism to try and like keep it at a readable level. So yeah, lends itself to it's hard to write good physics communication when talking about quantum mechanics. Yeah. Okay. Well, if there's nothing else there, and again, another short tutorial, but that is everything. So this assignment is pretty straightforward, as you guys have seen. Just either read the paper or take the interpretations off the paper and write short paragraphs about it. And that is due tomorrow at 11:59. So that is everything I have for you this week.
Is it just like a short summary?
Yes. Yeah. Absolutely. Well, yeah. The first part is explain the experiments. Sorry, didn't mean to draw through it, but explain the experiment in your own words. So take whichever way I interpreted it, or whichever way I said it, or which way you read about it, and say this is what happened in the experiment. And then the next paragraph is what you thought about the experiment, any questions you had, just anything that follows up on the actual experiment itself. So your own personal interpretation of the things. So.
Could your interpretation be the same one as, like, I guess theirs or anything?
Yeah, I mean, yeah, you could take the same one or the opposite if you want to. If you say that this is all like baloney and it's not, it's there's many like
It's a conspiracy.
It's conspiracy. Absolutely, you're welcome to take any interpretation you want, even if it's not justified by anything. You're welcome to your own interpretation. So.
I also didn't know. I thought I saw it. Is there a word limit or something? It's just 2 paragraphs.
No, just says 2 paragraphs. Welcome to write more. I will just be, I'll just have to read more. But you try and keep it around, 1 page, 2 paragraphs, and
Okay.
it doesn't have to be anything long.
So
or short.
around like 1 page-ish or something's okay.
Yeah, absolutely. Yeah, if you want to write more, go for it. But 2 paragraphs is at least the minimum that we're saying here. So,
That sounds good.
all right, I will get that. Stop the recording.